think we can start. Hi, everyone. Welcome to today's session. I'm Anvesha. I work at Hasgeek, and so the session has been organized as part of the Antil Insight community. The Antil Insight community looks at various use cases of AI, challenges in developing them, deploying them, and then again, risks associated with the same, and practices, strategies to mitigate them. So a lot of our focus is on currently around risk mitigation, ethics, policies, regulations, and things like that. So obviously, deepfakes have been quite popular, or rather unpopular at the moment. And so, as a way to sort of discuss issues around deepfakes, ways to detect them, even regulatory concerns and other detection methods. Um, we have been organizing a couple of sessions on particularly focused on deepfakes. So around last month, we had a talk on the policies and politics of deepfakes, and today we'll be talking about deepfake detection techniques. So we have Gautham and Romit today. They're both machine learning engineers and researchers, and they've been working on audio deepfake detection. They've recently published a paper on the same. I will drop the link to the paper in the chat in a bit. So how this session is going to go is Gautam and Romit will do a presentation, and then our moderator Romano, she will ask a couple of questions. If the audience has any questions, you can drop them in the chat, whether you're watching from YouTube or on Zoom. And yeah, that's how it's going to go. Over to you, Gautam, Romit.
Awesome. Thanks, y'all. So today we're actually going to be talking about the creation and detection of deepfakes. So, if we could hop to the next slide. So a quick intro about ourselves. We're both ex-researchers from Berkeley, where we used to work as part of Hani Farid's lab. At the time, we predominantly focused on audio deepfake detection, but now we're both kind of working on AI-generated images and video detection as well. If you could hop over to the next slide. So just to quickly go over what we're going to cover today. First, we're going to understand the threat landscape. So we're going to cover real-world instances where generative AI has been used for harm, and we're going to gain a high-level understanding of kind of how these technologies work and how these deepfakes are actually created. We're going to also discuss the differences between authentication and detection and cover a handful of approaches for deepfake detection, forensics, media analysis. And then, as Anwesha said, we'll have some time for Q&A at the end. I guess hop to the next slide. One more. So social media is really the primary medium that we're seeing for the distribution of deepfakes and AI-generated content in general. And it's something that a lot of kind of influencers are really starting to take advantage of. Of course, this is not the first time that influencers have been using kind of manipulated content, right? Most photos go through some form of Photoshop or have been run through some filter. So we see like that's what made Snapchat big, right? But with generative AI, they're really able to do so, one, at scale and really use it in really interesting ways. There's, of course, AI upscaling, which, maybe increasing the quality of the photos, or they may be using AI to generate content almost from scratch. So the person you're seeing on the screen, Sahid SK, is probably one of India's leading kind of AI content creators. And he's made some really, really cool images. You'll see a lot of kind of Marvel collaborations, a lot of like Marvel and cricket collaborations, or you'll see like Kohli as a kid. So Gautham, you'll hop to the next slide. So one of the things that we noticed while kind of going through his profile, and this is true about a lot of these AI content creators, is that they will add tags. So you see on the right that they've had a hashtag AI art, hashtag Midjourney. And if you actually look at the image, if you look at the bottom right, there's actually a watermark on the image. And this is fantastic because this is kind of what we propose as one of the kind of major solutions, right? Is you have to make sure you label everything, make sure everything's watermarked. But what's interesting is if you look on the left, you'll see that the photo is actually taken completely out of context and used by someone else on social media to spread misinformation. Now, according to the fact-checking website, one of the issues with this image is that people are using this to show, hey, Modi doesn't know how to use a microscope, yet for some reason this is in the headlines, right? So whether it's media censoring or something. And even though like but not at all mentioning the fact that this is just an AI-generated image. So we see a lot of this because especially if you look at the left side, what you'll notice is the watermark is still there. But the issue is that, a lot of these kind of platforms and people who are on the Facebooks of the world are really don't have that media literacy to be like, okay, this is a watermark. Let me go look into what this watermark is saying, or let me do that kind of secondary analysis on this. So that it's absolutely reasonable to believe that someone would just outright take this information and believe it up front. God, if we could hop to the next slide. And we're really seeing this kind of throughout the world. So this image on the left is a fake image of a Pentagon explosion that came out kind of early on when we were really seeing the early proliferation of deepfakes. And this actually moved the US stock markets by quite a bit. Similarly, as you can imagine, with the war happening with Israel and Hamas, we're seeing a ton of fake content. Now, this one is really particularly challenging because there is actually a lot of destruction happening as part of this war and a lot of real horrific images as well. So we as the general public, as we're trying to understand what's actually happening there, the mixing of the real and fake images is becoming incredibly problematic. And even news organizations are having a really tough time figuring out exactly how to report on this because they're getting a lot of these fake images as well. And obviously they have to take this very, very seriously and can't be putting out fake images kind of in their news reporting. Gautham, if you could hop to the next slide. So we wanted to kind of give a quick overview of how these fakes are generated. So we're starting with images. We'll get to audio and video as well. So there's kind of two major architectures that are currently used to generate these image deepfakes at the moment. The first one is generative adversarial networks, or we call them GANs. So the two boxes I particularly want to focus on for GANs is this blue box and this orange box. So the one that says generator and discriminator. So the goal of the generator is to actually generate the images. So in this case, it's generating the X-ray from noise. And the goal of the discriminator is to actually predict if the generated image is real or fake. Now, the goal of the generator is to trick the discriminator, and hopefully the discriminator is going to say, hey, this is a real image. And based on the output of the discriminator, it'll actually update the weights of the generator to try and make better and better images. In essence, what this is really doing is that it's actually automating the digital forensic cycle, where someone's generating the image, someone's testing it, and then the generator tries to create a better image that's going to fool the discriminator. And you go in this loop until the generator actually fools the discriminator. Now, we're going to be talking about these at a bit of a high level because obviously you could have an entire lecture on just this alone. So Gautham, we'll hop to the next slide. Now, I'm sure most of y'all are particularly familiar with the kind of big text-to-image platforms, so the Midjourneys, DALL-E, Stability AI. They're all using a technology called diffusion, which is kind of far and away now the most state-of-the-art way to generate images. So the way that the diffusion method works is that the goal of the diffusion is to really learn the underlying distribution of data within the images. So when you're training these, you basically start with pairs of images and textual description of those images, and you apply the diffusion process. Here, you basically add random noise to the image incrementally until the image is just noise. So in this case, we're looking at the top row of the top right image. So you'll notice you start off with a real image, and over time you get to noise. Now, in practice, this is actually really quick because it's actually a closed form solution. So you can actually mathematically solve this just kind of through a formula. The reverse diffusion process is the second row where you go back from noise to an image. In this case, for each step, you basically have a neural net that's applying denoising. So you'll notice from xt going back to x0 on the second row, each kind of step has less and less noise in the image, and you kind of see the actual image coming back. Now, to introduce text to this, we do a process called text conditioning. So if you look at the second image on the bottom right, you'll notice the phrase Paris in Milky Way. You run this phrase through a neural network to get what's a text embedding. you can basically think of an embedding as a numerical representation of a form of media. So this can be text, audio, images, video, whatever. All it's doing is it's converting a media, which is like audio, which is not just numbers, and converting it to a set of numbers that computers can understand and actually do kind of like calculations with. So in order to embed the value of the text into the image itself, so that when you give a text prompt, it'll be able to generate the correct image, you traditionally just concatenate this text embedding with the image at each step. So that during inference, so when we're using Midjourney, for example, all we have to do is we have to provide a text prompt, and it will be able to go from noise to generate an image that is representative of the text prompt itself. Gautham, if you could hop to the next slide. So we'll also be discussing audio. So one of the big things that we've seen here in the US with the audio is that, similar to India, elections are currently in process. And there was an election in New Hampshire that happened recently, one of the US states. And there was a robocall that went out to 20,000 American voters of Joe Biden actually telling them not to vote. So we actually have a clip of that, Gautham, if you don't mind playing it.
Is the New Hampshire presidential preference primary. Republicans have been trying to push nonpartisan and Democratic voters to participate in their primary. What a bunch of malarkey. We know the value of voting.
So we want you to notice a couple of things. First of all, the voice clone is very high quality. It's capturing, obviously, just the tone of Biden's voice, but it's also capturing the kind of speed of conversation. He talks relatively slow. The intonation is incredibly good. It has his kind of accent down very well. And so, the US government agencies looked into this, and they actually found that a magician spent $1 to generate this voice clone using minutes of data. And this is something that we've seen really well. So this platform that the magician used, and we kind of use in our own research, 11 Labs, is incredibly good for very cheap and even seconds of data sometimes. You can make really convincing voice clones. And this is really, really accessible. You don't have to have any back-end knowledge of AI or machine learning at all to do so. It's just a website. So Gautham, if you don't mind hopping to the next slide. So the way that these kind of voice clones are really made is traditionally what you'll take is first take raw audio of the speaker and run it through a neural network to create a speaker embedding. So a voice clone, so similar to the text representation we talked about earlier, you can make a speaker representation. Now with this voice clone, you have to add text. So we can, similarly to previously, create a text embedding, join the two, run them through a neural network, and create a spectrogram, which is basically a time frequency representation of audio. This spectrogram can be run through a vocoder, which is basically a process that converts these spectrograms back to raw audio, and we basically get deepfakes. Now, this is obviously a bit of an oversimplification of the process. As you can imagine, that each one of these boxes can once again get its own slide and whole architecture. But this is the kind of overview of how they work. Now, a lot of these kind of platforms that are getting big, 11 Labs, for example, are not actually super open about what they're doing, but this kind of structures the research understanding of how everything is working. Gautham, if you can go to the next slide. So next, we did really want to talk about the lip sync deepfakes. So Gautham, if you don't mind playing the left video.
Hello, I'm not Anderson Cooper, and you're not watching AC360. Today, we're discussing lip sync deepfakes, a technology that edits people's lips in videos to match another audio, creating a fabricated reality.
Thanks. So Anderson Cooper is a very famous kind of newscaster in the US. And so we generated this deepfake. And the thing is that this only took us probably 15 or 20 minutes to generate. And we'll discuss the actual generation process soon. But one of the things that we've really been kind of seeing with these deepfakes is that there's actually like really legitimate and positive use cases for it as well. For example, even Indian political parties have been kind of using this technology to kind of translate their promotional videos into various languages over time. So Gautham, if you don't mind playing the right video.
नमस्कार, मैं एंडरसन कूपर नहीं हूं और यह AC360 नहीं है. आज हम लिप सिंक डीपफेक्ट्स के बारे में जानेंगे. एक तकनीक जो वीडियो में व्यक्तियों के होंठ को ऐसे संपादित करती है कि वे किसी अन्य ऑडियो के साथ मिल जाएं, ये सच से भिन्न एक कृत्रिम सच प्रस्तुत करती है।
Thanks. So in this case, what you'll notice is that Anderson Cooper's face, the only thing that we've actually modified is the lips and the kind of nose to chin. So Gautham, if you don't mind going to the next slide, we can kind of talk about how these are actually generated. So the kind of state-of-the-art technology right now in the lip sync space is a platform called retalking. And we want to kind of go a little bit into the details of how this actually works. So what you'll notice is there's three major inputs into this process. So first is this top left image of Emma Watson with this white box taken out. Now, this white box is exactly where we're going to replace and kind of change what the lips are doing based on the audio input, which you can see at the bottom right, which comes in as a Mel spectrogram, and the synthesized reference, which is basically used in order to gain the likeness of Emma Watson's face. So in this case, you basically take all three of these and you're able to basically use a process called inpainting, where you fill in that white box and actually generate the lips to move exactly like they should, conditioned on the input audio. Gautham, do you mind copying the next slide? So there's kind of a couple forms of this video deepfakes. This first is the lip sync deepfakes, where you just replace the lips. And then there's this kind of full face swap, where you implant someone's face onto another person. So if we look at this chart on the right, and we can look at the top row in particular, what you'll notice is this gentleman's, who is considered the source, we can actually put his face on the target, this lady, and the result kind of shows. Now, a couple of things that we wanted to mention in particular is that you'll notice is that the hair of the target remains. So you're just replacing the face. So the way that this actually works a little bit is that if you look at this left table, is that there's various ways to kind of map the face. So there's some very, very simple ones. So like the pose, for example, just has kind of 7 dots on it and handles just 7 pieces of information. Whereas once you start looking at the 3D mesh, you have 3 by 1,000 vertices. So it's storing a lot of information. So in essence, this is how this alignment process will happen, where we can map both the source's face, the target's face, and really kind of align them correctly. Gautham, if you don't mind going to the next slide. So we wanted to kind of show how this actually works in practice and how people could do this just on their own computers. So there's a platform called Face Fusion. And what this is basically UI for us to do exactly this, where we can provide a source image. In this case, we'll use Shah Rukh Khan, and we'll put him on a James Bond video. So Gautham, if you don't mind playing the video. Thanks. So a couple things that we really wanted to highlight is, first of all, anyone is able to do this on their computer and just download Face Fusion. You'll get this UI, and it's incredibly intuitive and easy to do. Secondarily, it's just a matter of configuration to use, right? So there's a couple of decisions you have to make in terms of like what technology you want to use for the face swap, or various kind of nodes and knobs that you can turn. But very easily, you can get very, very high quality fake. So in this case, you can tell with that video on the right, there's almost no artifacts. And it works incredibly smoothly. Gautham, if you don't mind hopping to the next slide. And what's really crazy is that this is actually possible in real time as well. So the video we're about to show comes from our research lab, and it's using a technology called Deepfakes Live. And similar to the previous one, it's something that if you have a powerful enough gaming PC, you're able to download this and generate real-time deepfakes yourself that can be integrated with Zoom, Team, Google Meet, everything. So Gautham, if you don't mind playing it.
All we are is dust in the wind, dude.
So the two people on here, the one on the right is actually Connie Farid, our previous advisor, and then one of our colleagues, Elliot. And this was all done in real time. And it's, once again, this is incredibly accessible. Gautham, if you don't mind, just going to the next slide. So we just want to mention kind of the text to video real quick. So in the past month, OpenAI released a blog where they introduced their new model Sora, which lets you provide a text prompt, and it will automatically generate the video. So Gautham, if you don't mind playing the video. And the things we want you to notice is one, these things are done incredibly well. So the fidelity is incredibly high. There's movement throughout the entire scene. There are definitely a couple of issues, and Gotham will be getting into this in a little bit later, but you'll notice that the physics of the world may be a little bit off, the reflections are off, but the improvement in this technology in the past year has been absolutely crazy, where you like the old Will Smith spaghetti video that I'm sure many of y'all have seen to this, the improvement has been incredible, and we expect that these to improve further as we go in time. So just wanted to make sure that we touch on this. So I'll go ahead and hand this off to Gotham, who's going to be talking about authentication versus detection and going into some of the actual detection methods.
Thank you, Romit. I will start off by introducing you all to some of the solutions that are there to mitigate the harms from deepfakes. And I broadly want to classify these into two approaches. They're active and passive. So active approaches involve authentication, specifically tracking and verifying the origin and history of media using provenance techniques. So the C2PA and the CAI have been working on this and technical standards for their implementation. But what this involves is usually using metadata and watermarks to kind of track the provenance of a file. It's important to keep in mind, though, that metadata and watermarks can be easily removed from media files. And so these are a necessary but not the complete solution. What we need in addition to active techniques is passive techniques or detection. They're called passive because they're usually done in response to a media file being flagged, and we run these analysis to identify evidence of manipulation in the digital media. These passive detection approaches, they use a bunch of techniques, but usually they're around numerical methods such as statistical analysis or frequency domain analysis. And more recently, they've also started using ML and deep learning models to do the classification. In terms of the taxonomy for these approaches, you can kind of think of them in two ways based on explainability. Some of them are the decision-making process is transparent and easily understandable, so we call them glass box approaches. And in some others, the internal workings are less transparent and harder to interpret, specifically when we start using neural networks. So we call them black box approaches. Explainability is really important if this analysis is being done, say, for example, in a legal setting or to incriminate a person. So that's where that comes into play a lot more. In terms of just approaches in modeling, we normally see that there's two main approaches that are taken. One is that of anomaly detection. So anomaly detection is a problem where you identify patterns that deviate from a distribution. In this case, we'll create a distribution of real videos and model something around it and look if a new video deviates significantly from that distribution, and label that as a fake if it does. We can also use supervised machine learning, where we get a bunch of real samples and fake samples and train a binary classifier, or we could even train a multi-class system where we try to identify the specific architecture that was used to generate it or specific types of manipulation. It's also worth noting that the role of an analyst is really important here. These algorithms don't work in the void and they're not perfect. So we always need a forensic scientist or an analyst to kind of review the output of the algorithm and put it in context of other clues or evidence to typically come to a conclusion if the media was deepfake or manipulated. So I'll start off before talking about deepfake detection, covering a few of the classical methods in forensic analysis. And let's start by just visual inspection, which can be a useful tool many times. So you might have all heard that there are telltale signs of AI-generated images. The most common one being that they struggle in rendering body parts, specifically arms and feet. In this case, you can see two images. They're both fake images from the war in Gaza that were being spread on social media. I think it was on X. And if you start looking closely on the image, on the left side and zoom into the feet of that child, you'll notice that there are just three fingers. And there are a bunch of other boxes here that highlight some of the other inconsistencies that make you review this as a fake image. Um, Typically, what we see is asymmetrical or misshapen features, body proportions being off, issues with texture rendering, etc. Um, so it's also important to keep in mind that visual analysis itself is not sufficient. So classical forensics took the approach of building a bunch of mathematical models of what we expect to see in an image and looking for deviations from that to identify if it was manipulated or not. So here is an example. This is from work done by our advisor, Hadi Farid. The image you see on the left side is a 3D rendered scene of what you would expect in a physical world. And it's illustrating this property that parallel lines in the physical world, when it goes through perspective geometry, uh, will start to converge to what's called a vanishing point. So what you see here is the vanishing point, and the square in the physical world would have all those blue highlighted lines as parallel lines. But when it goes through a camera, it's going to go through perspective geometry. And as long as it's on the same plane, all of those parallel lines should recede to the same vanishing point. Now we can use this analysis to analyze images. The image on the right is an AI-generated image of President Biden in a military setting. And you can see that there's a wall on the background. That wall is a parallel plane, and we can see a bunch of parallel lines on that parallel plane. When you start like drawing out those lines and extending them, what you will notice is probably that they're two separate vanishing points, when in reality, we should have expected those vanishing points to be really close or identical, with some margin of error. So this is one technique where, again, an analyst would have to come in, look at the image, reason about where those parallel planes are, and start drawing those lines to look for vanishing points. Similarly, there's techniques for 3D forensics where we can reason about lighting to see if an image is consistent or not. So in this case, we're specifically looking for patterns of lighting on an object to reason about the source of the lighting. And this work requires a certain amount of 3D modeling. So what you see on the left is a 3D modeled face of a person. Faces tend to be relatively easier than many other amorphous objects of 3D model just because there's a lot of research on it. So when you have lighting on the face, you can create a 3D model of the face specifically to compute these short arrows called surface normals. And when you have those surface normals and these small patches of uniform intensity, you can create a system of linear equations to reason about the direction of the light source. So this technique is applied to the image on the right side. What you see there is, again, a Midjourney generated image, Midjourney or DALL-E generated image, but something that went through the diffusion process. And you see that while the image at an initial glance looks really realistic, it's violating the laws of physics in terms of the lighting. So this is in an outdoor scene, and you would expect that the sun is behind the person, given that the shadow is in front of the person. But when you do this lighting analysis on the face of the person, what you start seeing is that the brightness is kind of localized around the front of this person's face, which if the sun was indeed behind the person, that is a violation of physics, that the person's face cannot be that bright unless there was like a really bright source of light in front of him. So this is again kind of a contrived example for the sake of describing this technique, but you can start to see that, there are ways uh, where an analyst is required, where it's explainable, and we can model a bunch of physical phenomena to reason about images. It's also worth mentioning that analysts can do file forensics. So file forensics are simple techniques like on the left, you see a metadata dump using a tool called EXIF tool, where you can get a bunch of metadata about images. And these can sometimes have telltale signs about if the image was real or generated by AI. For example, many cameras will put the actual camera model in the EXIF metadata, which can be used to reason if that image was taken by a particular camera or not. On the right side, you'll see that we can also use things like JPEG quantization tables or JPEG packaging, specifically because different cameras and different image editing software use different quantization tables for compressing files when they're saved as JPEG. So these are some of the techniques that can be used uh, in addition to the previous techniques. Um, Most of the techniques that I discussed before come from classical forensics and have been used to detect image manipulation for a long time. There are a bunch of other techniques that we haven't covered, including reasoning about shadows, reflections, etc. But we'll move on to talking about deepfake detection, specifically computational techniques to detect not just image manipulation, but also audio and video manipulation. So another taxonomy here, deepfake detection can be broadly classified into three categories based on the approaches that are used. One of them is the artifact-based approach, where low or high-level features, including features such as pixel level inconsistencies, frequency domain inconsistencies, or noise patterns, are explicitly designed to then reason about if the media is real or fake. There's identity-based deepfake detection, where soft biometric style features or personalized features to an individual can be used. This is particularly useful in the case of, for example, world leaders, where there's a lot of real content about them. And then finally, we'll also talk about learning-based techniques, where deep learning or machine learning features are explicitly learned to classify real from fake. So I'll start off by discussing this in the context of an audio forensics problem. Um, in the initial slides, Romit introduced voice cloning. During the final semester of our graduate work, we noticed that voice cloning was blowing up quite a bit. So our lab worked on a paper to detect these voice cloning technologies, and we published that work at the workshop on information forensics and security. I think Anwish has linked the paper in the chat if y'all want to get a link to it, but I'll start walking you through the approach that we use there. So what we focused a lot on was classifying real audio from fake audio. Um, and most of the work we did was in handcrafting the features for training a downstream classifier. So I'll first talk about these feature generation part. We explored three different approaches to generate these features. The first one was where we listened to a lot of real and fake audio, and we started noticing that there were issues in the fake audio where um, the pauses were shorter and fewer, the amplitudes tended to vary, or in short, we noticed that, when we listened to a lot of audio, that there was a difference in the cadence for the same speaker in a real and fake audio sample. So we tried to model that using what we call perceptual features, which are low dimensional, can be understood by the average listener, and are easy to interpret. We then used an off-the-shelf library to get a bunch of spectral features. This library ran signal processing to extract features such as the Mel frequency capsule coefficients. It also got a bunch of time domain features like zero crossing rate, and essentially gave us about 3,000 odd features that we then did some feature selection on. Finally, we also used a neural network to extract embeddings. Specifically, we used NVIDIA's TitanNet to get an embedding for each audio clip. And once we had these three set of features, for each set of input features, we kind of used the machine learning process to separate it into a train validation and test set and ran it through a downstream classifier. We used both a nonlinear classifier, a random forest that is, and a linear classifier, which is logistic regression. And we measured performance in terms of accuracy. So in the lab, and by that I mean when we took pristine audio samples that came right out of the generation architecture, we noticed that the learned feature approach and the spectral feature approach, the performance was almost 100%, where on our validation and controlled test set, the accuracy was 100% in classifying between real and fake. On the perceptual features, though, we noticed that they didn't perform as well as the learned and spectral features. And our hypothesis was that we needed to spend some more time in engineering these features more robustly. But where it gets interesting is we then simulated the performance of these models in the wild by doing what's called adversarial laundering. Adversarial laundering is just this technique of applying transcoding and adding noise to kind of corrupt the artifacts or make it confusing for the downstream model to latch onto the artifacts that it learned. This transcoding part is specifically important because media, when it goes through different platforms, such as WhatsApp or when it gets uploaded to YouTube, undergoes different types of transcoding. And we ran these experiments to see how robust our models would be to these kind of transcoding. In the limited laundering that we did, that's specified on the left, what we noticed was that immediately the learned and spectral features took about a 5-point performance drop, and the perceptual features took a much larger performance drop. So the key message I want you to take away from this slide is that when we do kind of artifact-based forensics, robustness to transcoding and adversarial laundering by adversaries is something that you need to keep in mind of, because most people will report performances that are not robust to this. So another technique for doing media forensics is what we call personalized media forensics. So this was work done by Hani Farid and one of his students in his research lab, where they started analyzing videos of President Zelensky, specifically when, during the start of the war, a deepfake went out of the president claiming that he was surrendering. So in this approach, we use what's called a soft biometric for the person. And how this is done is by modeling the behavioral mannerisms specific to a person. In this case, we used OpenFace to extract 20 facial mannerisms of President Zelensky. You can see that in the top box here. We then used Blaze Pose and MediaPipe to extract gestural mannerisms, mainly the movement of the person. And then finally, we extracted the Mel frequency capsule coefficients to model the vocal mannerisms. And we correlated these features to generate a set of about 780 total features that was then used downstream in a classifier. So in this case, since there weren't a lot of fakes of President Zelensky, this was set up as an anomaly detection problem where a one-class nonlinear support vector machine was used for novelty detection. And essentially, you can think of a one-class SVM as defining a boundary around the correlations that we saw in these features in the real Zelensky videos. And so when you got a fake Zelensky video, the hypothesis is that that would fall outside of that boundary and would be classified as an anomaly. Um, Finally, I also want to cover end-to-end learning and its growth in deepfake detection. So this slide is from a review on the literature related to deepfake detection, published a couple years ago in IEEE. And you can see that about 77% of the papers that talked about deepfake detection use some form of deep learning. Machine learning and statistical methods were still present, but deep learning seemed to be the go-to solution for most researchers working in the space. So I think uh, I want to kind of explain the difference between what I mean when I say a machine learning approach and a deep learning approach. In a machine learning approach, here I'm using a contrived example of an input being a car and classifying it as a car or not. You can think of this as the same for fake or not. In machine learning, we have uh, researchers or experts in the field kind of reducing the high dimensional media feature space by performing feature extraction to a lower dimensional set of features, which are then used in downstream classification models, typically something like a random forest, logistic regression, etc. In deep learning, we get rid of that explicit feature extraction step and we let the network learn the features itself. The classic example is a CNN and image classification, where you let the CNN learn the filters by providing it large amounts of data of real and fake or whatever is the class that you're trying to classify. Um, so once this is set up, the machine learning process or the deep learning process, what we're trying to do is learn this function f of x, which acts kind of like a black box. And the goal is to input an image or an audio or a video and then get a score at the other end and a label associated with it. In this case, a label of 1 for the positive class that's fake and a probability score associated with the model's confidence. This is done using classical deep learning or machine learning approaches where we learn the parameters theta of a model by using an approach such as backpropagation. For image classification, what we tend to see is that there's a bunch of pre-trained image classifiers. These are all bundled up with PyTorch and have all been trained on large data sets such as ImageNet. So we're able to leverage transfer learning in this approach to use these classifiers downstream to classify images or extend that to other kinds of media as real or fake. So this is kind of where it's at. This is what you'd see with a lot of the public tools out there and a lot of models where, going back to that Gaza image, rather than reasoning about it and the geometry, etc., you provide this image to a neural network and the neural network outputs a score. In this case, it says that the model is AI generated with an 88% confidence. So kind of want to wrap up by quickly touching upon some of the research directions that are there in the existing research directions in deepfake detection. So we have to realize that this is a constant arms race and we're constantly in the need of new models. This is always true of anything forensic. When a new detection technique comes out, the adversary is going to try to beat that detection technique, and it's a constant arms race where the adversary and the forensic scientist are continuously trying to outpace each other. Robustness to transcoding and adversarial attacks, like I mentioned earlier, is an important research direction. We want these models to not just perform well in the lab, but also perform well on media that's undergone a lot of transcoding or compression, etc. Um, Generalization is another key area of research. And by generalization, I mean that a model trained on a limited data set generalizes well across diverse data sets. This is typically measured by uh, evaluating the performance of a model across different data sets. A multimodal detection is another one where different modalities such as audio and video are combined to do the detection. Explainability is big, especially where source attribution or decision making, like in a legal setting or in courts of law, etc. And that's another a big area of research in the deepfake detection side. And finally, I think doing digital forensics at scale is hard. Um, Getting the one-off video and sending it to a lab or an expert to review it has always existed and will continue to get better. But we're also seeing with the onset of social media and the scale at which this is propagating that we need to do this at social media scale. So this involves a combination of the active and passive approaches that I discussed, and probably some other solutions as well. Um, so yeah, that's it from our end, and I'd like to open the floor for questions.
Hi, so we have a question from Denny in the audience asking if we think that despite being more primitive statistical methods, do you think they're better suited for deepfake detection, given that it's easier to reason about it and explain it to people?
So that's a good question. I think you know, all of these methods have their place, and I think statistical methods usually tend to be more explainable if they don't latch on to artifacts and if they exploit things like soft biometrics. They're also robust to kind of transcoding to some extent. Um, but the downside is that, they usually, unless it's a very model-driven approach, um, the geometric analysis and the analysis that I discussed always requires a person to come in and do the analysis, which can be limiting when you think about analyzing this at social media scale. It would work well if there is, say, for example, a video of a world leader, or there's a media file that needs to be analyzed for a court case. But at scale, it can present some challenges.
Would you like to delve deeper into what are some of the challenges that you face when trying to do deepfake detection at scale?
Yeah, Romit, do you want to take that one?
Yeah, sure, I can do that. So I think the one of the biggest challenges that, especially we've seen that in the wild, is that there's a number of different mechanisms to generate deepfakes, right? So for audio, there's many different platforms. With video, there's many platforms, and with images, it's probably the most. And when you see something in the wild, you don't know whether it's a deepfake, and even if you do know it's a deepfake, you don't necessarily know what source it came from. And this becomes a training challenge, as you can imagine, right? Where when we're building these models, especially these kind of AI-driven models, we have to be really careful to try and make sure that we capture the distribution of all the various like 10s and 20s and 30s of architectures that are out there, because the second that a new architecture comes up, that data really becomes out of distribution. So it's not just about creating this super cool model that can detect deepfakes in the lab or even the ones that are currently out there. The biggest challenge is also just keeping up with the technology. As you can imagine, right? Like, I mean, Sora is going to be a perfect example. Like, people are going to have to almost like retrain a lot of what they have just to account for that. Or as the next innovation happens in voice cloning, right? I would be shocked if the models perform particularly well on this. So to Gotham's kind of cat and mouse chase thing, I think the greatest challenge is that innovation keeps happening on the generation side as well. And it's our job, and probably the most challenging part is to kind of keep up with that.
Thanks for the answer. We have another question from the audience. Pranjal asks if there are any tools available for a non-technical population to identify audio and video deepfakes, and would you suggest some links for the same?
I think there are a bunch of tools that are proprietary that might have that provide these services, and there's also a bunch on GitHub. I think for the non-coder GUI base, is there anything that comes off the top of your head, Romit?
I mean, there's a number
Yeah.
of platforms out there that are working on this, right? Or like the
Mhm.
reality defenders out there resemble AI. We will caution against those a little bit, at least from our testing. Performance is okay. I think rather one mechanism to use is if you think that there is one, you can use this kind of as a double check. But even we caution a little bit about blindly using those tools and actually trying to use some of the things that we discuss, like oftentimes the shadow thing is something that you can actually see. Look at the hands closely. The technologies are getting better and that's becoming harder and harder to do. But as of now, those still hold. So we definitely like there are tools out there, but we definitely caution against having blind trust in them because these AI models, they'll never be 100% correct. And kind of going back to the explainability conversation is we have absolutely no idea what some of those are latching onto, especially these super proprietary ones. So
Right.
Yeah.
What was the time cycle like with, yes, please.
I'm sorry, could you
With employing tools that were more technical in their nature and involved a bit of coding, what was the time cycle like for from the process of starting to being able to actually reasonably with accuracy detect a deepfake?
I think well, it depends in the sense that right now, going back to a lot of these tools that are out there that have are basically model driven, you can get results pretty fast.
Mhm.
But these models, like Romit mentioned, we don't really know what they're trained on. And they claim some accuracy numbers, but we don't really know what distribution they're trained on. So the way we think of it as people operating the forensic spaces. There's just one tool that'll give us one input, but you need to use a variety of other tools. Some of these tools are slower. Like for example, the not necessarily slower, but require manual intervention. So the geometric analysis, you kind of have to set that up, and that code is there's MATLAB code for that available in Hani's book, but you'd have to set that up and run the analysis and reason about it. There's a bunch of other tools that are open source that you'll have to maybe train. Say, for example, you're using a model that was our model that was in our research paper. We haven't explicitly trained on Indian voices. So if you're trying to use it to reason about, say, an audio clip of Narendra Modi, then you'd have to get more Hindi data or like Modi speeches and retrain the model on Modi speeches. So, there's a bunch of things at play there, which is why I stressed on the role of a analyst or like a forensic scientist being in the space where they can look at these different tools and reason about, put that accuracy or the result in context along with other clues.
I'm assuming any speed here then comes from transfer learning, and then that depends on how close the data set is to your actual, and that kind of results in.
For image classification, yeah, definitely transfer learning does give some speed in the sense that, rather than starting from scratch, training on an ImageNet pre-trained backbone is definitely helpful. But I guess I understood your question wrong. I thought it meant speed of analysis and not speed of training the model.
Right, but I was just saying that if the model is trained to kind of detect for the data that looks like your data, then a lot of the speed in the analysis is being eased by that. Like you said, like if it's a Hindi speaking population and we don't have the data available right off the bat, especially in formats to straight up train it. So some of
So
the
definitely, so going from scratch, from like having no model to having a model, the interesting thing is that the bottleneck for getting the model ready really isn't actually the model training itself. It's rather data curation, right? Kind of like we were saying, there's like, there's many different architectures out there that are generating these things. There's a ton of different sources where they're coming from, kind of like how Gautham said, right? Every platform has its own transcoding and kind of data preparation. Some places remove metadata, some places, will compress their audio or video like crazy. So in order to create a good model, we need representative data that we're going to see in the real world, which means that for every single thing, we need to know what Facebook is doing to the data. We need to know what YouTube's going to do to the data. And then we need to be able to either scrape data from there, which is already questionable, or what rather how we handle it is we try and mimic those same kind of actions on our data. So what you'll find is, and I'm sure this is true about most research labs, is that they're spending the vast majority of the time on the data, not necessarily even the model. Right, we can make model tweaks and we get small performance gains here or there, but really the secret sauce to any of this is data.
right. And what has your experience been with multimodal detection? Has it been
It's
better?
I think multimodal detection is definitely one of the new frontiers in this space, and it is challenging. I mean, just thinking about it theoretically, it should offer better performance because you're combining different modalities. The lip sync deepfake, for example, listening to the audio and looking to the lip movement, etc., can give clues. Um, but it is an emerging area of research, and there's I'm not aware of anything that is um, probably using multimodal stuff for commercial applications. I've mostly see it in research papers around deepfake detection.
But do
It's
you see
also
some,
sorry, go ahead.
uh, I was just asking if you see some of those techniques translating to the AR and VR space and being able to work for like even more multidimensional data, for example.
Oh,
Um,
I haven't seen anything in the AR VR space yet. Because again, I mean, when you're dealing with media, it's also worth noting that the computational demand is really high, which makes it really hard. Dealing with tabular data is usually a lot easier, but creating complex vision and audio pipelines for both the generation and the detection side requires a lot of compute resources. So I haven't really seen, I mean, most of the people who are writing these papers or doing the research focus on immediate harms, like, to world leaders, to people of important, like, in important positions, and also try to generalize it to the normal public and make it more accessible. I
right.
haven't really seen much on the AR VR side.
Do you have any tips for the general population for protecting themselves against uh, deepfakes being created against them or not being able to, like being misinformed by, for example, WhatsApp feeds and so forth?
I think media literacy is the big one. I definitely want more important people talking about deepfakes and educating people that this is a threat vector that exists, and, you know, um, making them skeptical about content that they receive. Because, one of the reasons deepfakes work is because of this thing we call processing fluency. You always want to believe that what you're seeing is real, and up until recently, we didn't really have, photography or videos were kind of like evidence of the real world, right? There's Photoshop and stuff, but there are more color correction, and manipulation wasn't a really big thing. So, people are used to processing fluency, people are used to just consuming media and reinforcing their biases. So, just educating them that, media can be fabricated these days, uh, and relatively easily by pretty much anybody who has a powerful computer is one big step. Um, Other than that, hopefully these tools will start developing to a level where, We can put it in the hands of these people, so they can upload media content and then start verifying it as well.
Right. Has the application of deep learning techniques really improved the ability to detect deepfakes? Has there been a quantitative jump?
But Romit, do you want to take that?
Sure, yeah. So I mean, we could actually even go back to the slide from our paper with the kind of performance numbers, where what we're finding is like the deep learning has had an incredible impact, right? Because part of the challenge, right, is that these are very like just audio, video, these are very data-rich mediums of information, right? Like you can imagine, like even a photo is 256 pixels by 256. You can do that multiplication, you can imagine how much data that is. And deep learning really just has this kind of unique ability to be able to process things and find things in a way that we as humans kind of struggle with. That being said, right, where I think a lot of the real magic is the real combination of using human intelligence and this deep learning, right? Sure, you could just toss in, if you're doing image classification, you could just toss an image to deep learning and give enough images, it will probably learn it. You know, it's a challenging training exercise, but you'll probably learn it. But if there's ways that, you know, we can use our understanding of images and pre-process it in a way such that we can make it or make it easier or more obvious for a way that the model can latch on to something specific. That's where we think it's like deep learning and kind of our own intelligence can really play a role. It's all about reducing the feature space, right? Make it as obvious to the model what we think is valuable for the model to latch on to.
Right. So, since the legal precedent still favors explainability in a court of law, as Gautham was saying, when somebody is being implicated, so do you see that changing in favor of machine learning approaches?
No, rather, I think it's going to be the opposite. I think that explainability is going to become a major piece of these AI models. Right now, explainability research is probably one of the top fields of research right now. Almost everyone's trying to do it. So if I had a crystal ball, I would probably guess that this explainability is going to get better and better. And over time, you know, these models will actually be telling us exactly what it's honing in on. And it's going to become our job to try and figure out like exactly what the model is doing based on its explainability output.
Right. If the audience has any more questions, we'd encourage you to ask. And is there anything you'd like to delve into deeper? Anvesha's back. Hi, Anvesha.
Hi.
Um,
Yeah, I don't think we have any questions from YouTube or anywhere. So if you have any closing thoughts, please go ahead.
yeah, I mean, I think, thank you for the opportunity for letting us present this. And we think that, this is an area of research that is pretty new, and both of us got involved in it like probably a couple years ago, and we've seen rapid changes. The generation side is just moving really fast. The adversary is moving really fast, and these tools are becoming really accessible. So, we hope you can educate more people about this threat, and that more people are interested in doing the work that we do, which is on the detection and risk mitigation side of it. Romit, any closing thoughts?
No, I think that was great. Thanks. Thanks, Sam, for having us. This was fun.
Thank you. Thank you so much. Thank you for joining us early in the morning. And yeah, everyone else in the audience, thank you for sticking around. It was a great talk, very insightful. And thank you, Romano, for moderating that. The conversations were great. Yeah, I think this video will be up for anyone who wants to watch it at a later time. And we will keep having sessions around AI and risk mitigation and ethics and all of that fun stuff. So yeah, keep an eye out, and I think that's it. Good night and good morning.
Awesome. Thank you, everyone.
Thank you.
Yeah.
Bye.
Bye.
Bye.